Thank you, Eugene. And let's get the show on the road. We have about an hour and a half, which we're going to explore the whole excitement of science, the excitement of the discovery of last week. So I'm going to start by just introducing very briefly the panel. Now, on my extreme right, on your left, is Stephen Myers. Now, Stephen is a native of Belfast, and his title is Director of Accelerators and Beams in CERN. In other words, he owns the machine and runs it. Well, he thinks he owns the machine. And those of you that were down in the convention centre this morning will just realise what I was doing and what it does. And the people who were here earlier this morning would have seen a video running here, and they were shots from the experiment that took place and which led to last week's great excitement. Beside him is Rolf Dieter Höher, and he is the Director General of CERN. Now, what does that mean? It means that everybody else who works in CERN calls him Sir. Except me.
No other exception.
And he's going to be immortalised for 3 words that he said at that famous press conference, "We have it." So, he has it. On my extreme left is Frank Close. And Frank is Professor of Theoretical Physics in Oxford, and not only being a brilliant physicist, he's a brilliant communicator and has written many books on physics. The 2 most recent ones were Cosmic Onion and Infinity Puzzles. And as we'll learn in the discussion, you'll see what science is only good if there's no making a discovery unless you can communicate your ideas to the public. And that's very important. That's where Frank excels. Next to Frank, we have the famous Baruch, and he's an experimentalist in physics, particularly in detecting of particles, and that fits into the whole thing. So Frank gives you the theory, Stephen gives you the equipment to do it, and Thames will measure the experiments. Of course, with the permission of the general. And finally, on my left, finally, not least, is Tara Steers, and she is a reader in University of Liverpool, and like them, they're both visiting in University College Dublin in part of this collaboration in particle physics with Ronan McNulty. So that's our panel, and I'll start off by try to get a discussion going. And then if we get the discussion going, then it's over to you to ask the hard questions. And if you don't ask the hard questions, it'll come back up to me and I'll ask the easy questions. So let's go back and see where we would start. And I was thinking that if you go back to 1931, I'm not that old, but I did read about it. You all probably have heard about the decay of radioactive particles decaying. One of the ones they looked at was beta particles. And when beta particles came out from a radioactive source, what they found was they all didn't have the same energy. They had a whole range of energies. And that puzzled people. Why could some of them have a lot of energy and some have very little energy? So a man called Pauli in 1931 postulated that there must be something else taking care of the missing energy. And he postulated a thing called a neutrino. And it wasn't until about 25 years later that Riens and Cowan actually discovered the neutrino. So that's the premises. First thing, it took them only 25 years to do it. Now, I think it was 1964 that Higgs proposed the Higgs boson. And it's taken nearly 48 years to do it. So why was that? So we'll start off by saying, what is the difference between the idea that was around at the time of the beta decay and the postulation by Pauli of the existence of a neutrino and where we are today? So I'll throw that over to the panel, and who wants to pick up the ball and run?
That's Frank. This is like being in a PhD oral exam with people listening, isn't it? But yeah, why did it take 48 years? Because the experimentalists took so long. Pass the thing back there. I mean, what is it that has been done here? It's something remarkable. Earlier this morning, I actually showed exactly 100 years ago where Rutherford and Geiger, who discovered the atomic nucleus in 1911, was standing together in their laboratory in a little room with the apparatus that did it on the table. And I was asking, why is it so, quotes, easy for them as compared to what we're doing today? And I think the main difference is that we were trying to understand what matter was made of, and what Geiger and Marsden were doing was looking at matter that had been coagulated for the last 10 billion years. And relatively easy to tickle it and see what's inside it. What we now have been doing is trying to understand where everything came from. And the best theories that we had made no sense unless you pretended that everything was massless, which is not a very good approximation to the real world. But in 1964, Peter Higgs and several other people, to be fair, found a way mathematically of getting mass into the theory without the whole edifice falling apart. Only Peter among those pointed out a consequence of this, which is that there should exist a massive particle which lives for a very brief moment, named after him, the Higgs boson, and the decays of this particle could be used in an experiment to see if that's how nature really does things or whether it's just clever mathematics. And we now know that is indeed how nature does things. But why did it take 48 years? Because the Higgs boson, which we now know would have been very common in the first trillionth of a second of the universe, it's not that easy to go and do an experiment to recreate the first trillionth of a second of the universe. You don't go to your local science shop and say, can I have a Big Bang apparatus? It takes 20 plus years of people all around the world, I mean, Steve and Dennis can tell us more about this, working together collectively to build this incredible piece of technology. And 20 years ago, if you'd asked me, is this going to happen, I would have said probably not. So I think, to me, although I'm a theorist and should be advertising the Higgs boson, I think that this is a triumph of engineering, primarily. It took that long because to recreate those conditions is very hard, and it's only now that we've been able to do so.
Could I just butt in there? I mean, first of all, I think people started looking for it pretty quickly, actually. I mean, I remember in the 70s they were looking for it. I remember moving to an experiment because they thought they had it. It turned out that it wasn't as accessible as we thought it was to our experimental equipment, and it took us 20, 30 years and many different experiments to finally get to the point where we could get to the right energy, create the right temperature, create the right environment to actually spot it. And I actually think, given the complexity of the problem, 50 years is not very long. It might sound like a shocking thing to say, but it's actually quite a short time for what we've achieved.
Maybe one should add that although all the properties of this famous particle were predicted, can be very well be predicted. The only thing which could not be predicted was its mass, and therefore one had to scan, so to speak, the whole mass spectrum. So one started, of course, with a low mass, because at that time one could have accelerators of lower energy, which could have produced particles with lower mass. But then finally one found out it is heavier than one thought, it has become even heavier, etc. So we needed a technology which was not there 2 decades ago. And finally we found it, and one should also say it is much lighter than one thought originally then also, yeah? I mean, it is a heavy particle, it's the second heaviest fundamental particle we know, but it is, in principle, a light particle. Yes.
It's lucky that it's at the light end of what the LHC can reach. Thankfully.
We thought we had it in left. We just couldn't squeeze any more energy out of left to get it. We reached 114.5 and it was about 10 GeV unfortunately. But there was a lot of excitement in 2000 when we thought we had it.
And you might wonder why, given that it's taken us 50 years to find this, why you would ever stick around looking for it for 50 years. But it's because it's of such fundamental importance in our understanding of the universe. Frank has said that it's the only explanation we have for why particles have mass. And that sounds small and simple, but that is the reason why the universe looks the way it does to us. It's the reason why we have atoms, it's the reason why we have planets, and it's the reason why we're here today. So the Higgs is part of the fundamental fabric of not just the universe, but it's intrinsically important to our understanding of it. And that's what's driven our research very much for the past 50 years, getting that deep understanding, not just to understand the Higgs, many questions beyond it as well. But that's what's driven our whole technological push to build this really complicated machine. And it has taken thousands of people, many, I don't know, 100,000 man-years of effort, but here we are today, we finally found it. it's quite an amazing achievement.
To me, it's fundamentally different. It's not just, I mean, sometimes people accuse us of simply peeling back layers of an onion, and infinite layers of an onion, and just keep going on, okay, so you found another layer of an onion. I think this is fundamentally different. I'm probably frank and confident that this is a fundamentally new, different thing. It's not just another layer in the puzzle.
Well, it's probably the end of a chapter in that we now are able to describe all of the stuff that makes you and me, which sounds great until I tell you that's only about 4% at most of everything there is. Because there is a lot out there that we are aware of but don't know what it's made of, stuff called dark matter. We know by the way the galaxies pull on each other, there's a lot of stuff dragging the galaxies around by gravitational force, but it doesn't shine. And what it's made of, we haven't got a clue, because there's nothing in the present stuff that we know of that has the right properties. So dark particles, whatever they might be, are presumably waiting to be found. Whether they are within the reach of the LHC or not is the big question. And the analogy that I've been drawing is that if we're trying to find that question's answer, it's like finding the gold fields of California. What we have done is, having been told that North America is there, we have now found it and landed. But whether we've landed on the east coast or the west coast, we don't yet know as to how near California it's going to be.